Okay, so one of the things that we've done so far is that we've looked at different ways of finding the transfer functions of circuits. So if you have circuits with elements, you can calculate them using the nodal analysis, you can do mesh analysis, you can do KCL, KVL directly, and all sorts of things. But one of the ways that's very useful and very effective, particularly when you deal with electronic circuits, but even if you don't, is the so-called time and transfer constants, method of time and transfer constants. So it's a way of calculating the transfer function of a system without actually writing KVL and KCL. Or more accurately, without writing high-frequency KVL and KCL. So you don't have to write anything in terms of the capacitors or inductors. So there's a way of doing this. Now, I'm not going to be able to cover all the details of that in this lecture. There are videos 137 to 148. So if you want to go watch those in the sequence from 114. But again, I'm going to give you a very brief introduction to this. So this is time and transfer constants method, or TTC for short. So I'll start with a very simple system. So let's start with a simple system. Let's say you have a first order system that has an x input x of t and output y of t. Let's say this is a circuit, specifically a circuit, right? Now, if it's a first order system, it means that it has one energy storage element or independent energy storing element, right? So let's say it has one energy storing element. Let's start with a case of capacitor. Let's call it C1. So if I take it outside this box, what's inside this box is purely resistive, and it consists of resistors, dependent sources, independent sources, all sorts of things, right? But it will not have any capacitors or inductors inside if I just take it out of the box. So we say no dynamics in this network, in what's inside the box. The question is, how can you determine the h of s? In other words, the y of s over x of s, the transfer function of this circuit. How do you do that? So there is a way to do this, and we are not going to prove it here. Again, you can see those videos or look at the paper associated with it that you have as a handout that tells you if it's a first order system, it can be written in this form. And I will write the full form, and I will explain what these terms are. So it's h superscript 0. These are superscripts. These are not powers. Tau 1, 0, h superscript 1 times s, complex frequency, over 1 plus tau 1, 0. So this is a subscript and superscript, s. So what this does, it says for a first order system, you can reduce the calculation of the high frequency transfer function to 3 low frequency calculations, which are much easier to do. The first one is H0, which is defined as H when C1, or if it was an inductor, or L1, goes to 0. So this is, the superscript is essentially the index of elements that are infinite value. So H superscript 1 means that it's the transfer constant. These are called transfer constants when C1 goes to infinity. And tau 1, 0 is C1 times R1, 0, where R1, 0 is the resistance seen by the capacitor. If you remove the capacitor and look across here, when you null all the independent sources, and this 0 also means null all the independent sources, 0 value everything, the sources, is this resistance times the capacitor. So this may look complicated to you again, but let's do an example, a couple of examples to see how this works. So let's start with something very simple that we understand well. Let's say you have a voltage source, Vin, going to a resistor and a capacitor, C1, let's call this R1 or R. And this is V out. So I want to determine what's the H of S. In other words, V out of S divided the transfer function. So that's what I'm trying to determine. So we need to calculate these three quantities, H0, H1, and tau10. Right? So what is H0? It's called the zero value transfer constant, you can call it. These are called transfer constants, these are called time constants. So what is H0? What's the transfer, what is H when C1 is 0? When you make a capacitor 0, what do you do to it? You make it, what's the capacitance with the capacitor, what is capacitor with the capacitance of 0? It's an open circuit, right? So if I remove this, what do I get? So this is the equivalent circuit in that case. What is V out over V in? What is it? If there's no capacitor here? What's the current through the resistor? 0. So what's the voltage across the resistor? So what is this voltage in terms of that voltage? The same, 1. Right? So H0 is 1. Right? So what is H1? Meaning when capacitance is infinite valued. What is the capacitance with the capacitance? What is the capacitor with the capacitance of infinity? It's a short circuit, right? So the equivalent circuit for that is this. What is V out over V in this case? 0. Okay, so there's one more thing we need to determine, tau. Which basically for that we need to determine R10, meaning the resistance seen by the capacitor when all the independent sources are nulled. So if I null the independent source, this is a voltage source, so it becomes a short circuit. So I'm interested in seeing what is the resistance seen across these two terminals. That's R10. What is that R10? No, look. You can connect these two if it helps you. What is the resistance? R, right? So it's R. Therefore, tau10 is going to be R1C1. So you already have the transfer function. You just plug it into this thing, and that gives you H of S is 1 over 1 plus R1C1S. So this is a rather trivial example, right? Let's do something a little bit less trivial. Now, let's do something a little bit more complicated. Okay, now, before I do that, though, let me tell you what the general form of this thing is. So this is, I mean, you could do it with inductor, so that's for the first order system. How about higher order systems? A higher order transfer function in general for an nth order system has this following form, right? A0 plus A1s plus A2s squared all the way to AM s to the m. And in the denominator, you can write it as 1 over 1 plus B1s plus B2s squared all the way to Bn_Sn. So you can show, and again, you can find the proof in the paper, that A0 is H superscript 0, meaning the transfer constant when all the elements are 0 valued. No element is infinite valued. As I said, superscripts are the indices of the elements that are infinite valued. Now, A1 is going to be sigma, or let me write the B1s first. B1 is the sum of what we call the zero value time constants. So these are the time constants you see across each one of the n elements. So this is really for a system to think about x of t and y of t, where it has n independent energy storage elements, right? C2 could be L3, so on and so forth. So there are n of them. And this has no dynamics inside. So this basically covers essentially all kinds of circuits, right? Because you can actually view them as independent, as these inductors and capacitors, as things that are outside this box, and look at that. So this is basically some of the zero value time constant, meaning that you look at this resistor across here when all the other elements are zero valued, meaning the capacitors are open and the inductors are shorted. Because a zero valued inductor is a short circuit, right? And you look at that and you determine those resistors and you multiply it by time constant. So you can write it as sigma Ri0 Ci for I equals 1 to n. And now A naughts are essentially HIs times tau I zeros. So it's a weighted sum of this time. And then you can show later on, I mean, you can show that B2, for example, is the sum, it's a double sum. You can write it as I and j, where I is not equal to j, or I is smaller than, I'm sorry, so this is basically for I going for j going from 1 to n, and I going from n, or from j to n. There's another way of writing this, which basically saying it's the sum of I over I and j. I'll write it again. Tau I0, tau ji. Now, this is a product of two time constants. This is the same time constant. This is the zero value time constant for the element I. This is the time constant across element j when element I, which is in the superscript, is infinite valued. For example, so if this were 2 and this were 1, it means that you look across here and you make element 1 infinite value, which means that you short it this time and you see what the resistance is that you see here across here. And you repeat this calculation and then you find this thing. Again, you can write this sum in this form. I and j, I smaller than j. For tau I, 0, tau ji. And so on and so forth. So for B1, for A1, A2, you can write it in this following form again, ij, I smaller than j, hij, tau I0, tau ji, which is basically this term is similar to this term. There's an extra transfer constant in front. So how do you apply this? Let me give you another example with two elements now. Let's just pick something relatively straightforward. So let's say I'm looking at determining the transfer function of this circuit. Let's call this C1 and C2. And this is R and that's R. And let's say this is V out. And this is V in. So what is the transfer function for this? So let's determine what are the things that the things that we need to calculate. So the first one, let's determine H0 because that gives me A0. Right? What is H0? H0 is the transfer function, V out over V in, when all elements are zero valued. A zero valued capacitor is what? An open circuit, right? So you open circuit both of these capacitors. What's the output voltage in terms of the input voltage? What's the output voltage? If this is zero, this is open and this is open. 0, right? Because this is open, it's not connected to the inputs. It's connected to ground. So this is 0. Now, how about, and you can see most of these calculations actually are pretty straightforward, although the notation looks pretty complex. So how about H1? When C1 is infinite valued and C2 is zero valued. When C1 is infinite valued, means that this is shorted. And C2 is zero valued, means that this is open. So what is V out? Still 0, right? Because this is open, so it doesn't matter what happens there. Now, how about H2? When C2 is infinite valued and C1 is zero valued. Meaning this is short, this is open. What is H2? If this is open and this is short. 1/2, right? Because you have a resistive divider between these two. And what is H12? Meaning that when both of them are infinite valued. If this is shorted and this is shorted, what's the output voltage? 0, right? Because this is shorted across here, so nothing makes it to the output. So that's 0. So out of all these things, there is only one non-zero term. Let's calculate the time constants. So we can say, what is tau 1, 0? Tau 1, 0 is the is basically determined by this capacitance times the resistance seen by it when the other elements are 0 valued. When this is 0 valued, it's open. So this side doesn't matter, right? And all the sources are nulled, which basically means that this is shorted. So what is the resistance seen across here when this is open and this is shorted? R. So basically it becomes C1R or RC1. What is the tau 2, 0? What is the resistance seen by this guy when the other guy is open, 0 valued, and this is short-circuited? What is the resistance seen across here? 2R, right? Because you see 2R going around. Now you need one more of these things because of this J being smaller. So you can actually calculate one when the other one is shorted. So for example, you can do tau, if you use you can say tau 2, 1. Meaning the resistance seen across 2 when element 1 is infinite valued. So when I make this infinite valued, this becomes short-circuited, right? So what is the resistance seen across this when this is short-circuited? This is short-circuited too, but that doesn't matter really. What is the resistance seen across here when this is short? R. So it becomes RC2. So we're done. All we need to do is just to plug these things in. So you can actually write a transfer function, h of s, as A0, we know is 0 because H0 is 0. So that doesn't matter. The first term is A1. In fact, the only term in the numerator is A1, which is this. Now, the only term that's non-zero in this sum is the H2 term, right? So I write it as H2 tau 2, 0. That's what this term would be, the only remaining term there, right? And in the denominator, I have 1 plus B1, which is what? The sum of the time 0 value time constants. This plus that. Oh, this should be C2. So it becomes R times C1 plus 2C2S plus. Now the next term is this one. No, this one. This looks complicated, but it's just only one term, right? It's the product of tau 1, 0, tau 2, 1. Oh, let me write it in that form, actually. So this becomes tau 1, 0 plus tau 2, 0 s plus tau 1, 0, tau 2, 1 s squared. And if you plug these values in, you will get 1/2 tau 2, 0. Well, that cancels the 2, so you get RC2S divided by 1 plus R times C1 plus 2C2S, this plus that, times S, plus this times that, which is R squared C1 C2 S squared. So that's the transfer function. And it actually also becomes quite useful when you have transistor circuits, which we haven't covered yet. But there are examples of that in the handout that I gave you. And there are more examples of this in the handout, even with passive elements. So this is a useful thing in a lot of places where you try to determine the transfer function of a system. Any questions? Again, as I said, there's a lot more detail involved in this. So there are like 11 videos on that, and from 137 to 148, I think. Why was H0, 0, right? So to determine H0, means that you 0 value all the elements, right? Meaning that for capacitors, 0 valuing means they're open. For inductors means they're short, right? I can do one with inductors too. So what is the V out in terms of V in? Okay? Yes? Why is there no tau 1, 2? There is one tau 1, 2, but we don't need it. I didn't calculate it because I didn't need it. I needed one of them because of this j being smaller than I being smaller than j. So it's a sum from that point on. And is it arbitrary which one? You can choose whichever one is more convenient for you. Because if I had made, let's calculate the tau 1, 2, just for completion. What is tau 1, 2? Meaning, which one was C1? This one was C1, C2, right? So tau 1, 2 means that the resistance seen across here when C2 is infinite valued, which means that it's shorted. So what is the, and this is shorted. What's the resistance you see across here? 2 R's in parallel, which is what? R over 2 times C1. Now, if what I said was true, then I should be able to get this term either from tau 1, 0, tau 2, 1, or from tau 2, 0, tau 1, 2. So let's see if the tau 1, tau 2, 0, tau 1, 2 gives me the same result. So tau 2, 0 is this, tau 1, 2 is this. So the product of these two is also R squared C1, C2, which is equal to tau 1, 0, tau 2, 1. So you could do it either way. Right? It's pretty convenient. There are a couple of advantages. One is that if you want to determine the transfer function and all those things, you can do it. But the most important useful part of it is that there are many times where you're trying to approximate a transfer function. You're just trying to find what this first term is, this and that term. You don't need to, so if you want to do it the regular way with the nodal analysis, you have to do the whole calculation. Let's say it's a fifth order system. You have to do all of those calculations and all those, and you will see fifth order system, right? So you can all do, and then at the end of the day, if you haven't made any mistake in that grueling calculation, what you will see is that, okay, now I'm going to drop all of these terms and use this, right? So now instead, what this allows you to do is to calculate only the terms that you need, and make it accurate to the level that you need. You don't need to make it to the end. So you say, oh, if you're only interested in these two, you can just basically calculate these two and then don't do the rest of the calculations and get a first order result, which is what matters in a lot of cases anyway, particularly when you're designing. All right? Any other questions? All right. Okay. So that's it for that.